So let's go back to our neuron description. So the neuron description, we have a number of inputs, each one of them weighted by a different weight. So this is the sum that we have here, plus a bias. So this part of the neuron related to the inputs and the dendrites, they are just a linear weighting. And then we have all this information combined through that goes through a nonlinear function. We can see that this is a scalar value. So after all this will be just 1x, and this is g of x. So what kind of g of x we can have? So we could have an identity function. So identity is just not do anything. So this would be the response, the blue one. We can have a very popular one is ReLU. So ReLU is this function that is x times the Heaviside step function. The Heaviside step function is 1 if x is larger or equal to 0, or 0 if it is not if it is smaller than 0. So you have a step function, and that is represented here. So below 0 it is 0, and after 0 it is just the identity. And the problem with this function is that it's non-differentiable here, but up to that a small point where it is not differentiable, the rest of the function is fine. And then the problem with this ReLU function, it works for many problems, but sometimes it gets trapped into local minima, because when you are on this side, the derivative is different from 0, so you know where to go. But when you are on this side, you don't know where to go, because all the derivative, it doesn't matter how you move your weights, the output will always be 0. And so there is no gradient. And then you can have something called the liquid ReLU. So the liquid ReLU is this function in which you give a small slope to this part, so the rest remains the same, but this negative side has a small slope a. So you define the function on the positive side as the standard ReLU, and on the negative side, that this is this u of minus x, you define it as a ReLU multiplied by some small constant, typically 0.2 if you want, for instance. Then you could have other non-linearities. Logistic was used for a very long time. So logistic is defined between 0 and 1, and in this way. If you don't like this way, what you can if you don't want to be between 0 and 1, but between 0 or minus 1 and 1, or minus 0.5 and 0.5, you can simply scale and shift this function to fit your needs. Then you have, for instance, GELU. So GELU is it uses the CDF of a Gaussian that goes. It is a smooth function like the logistic one that goes between 0 and 1, and then you multiply by x. So this multiplication by x, this is the result of the GELU. And here I'm just showing 4 of these nonlinear functions, but you can put any nonlinear function. The interesting thing here is that there is some slope. When the function saturates the network, and the optimizer will not know where to go. So because it changes the weights, and it sees that the function almost doesn't change, so it doesn't know where to go. So having 0 slope is not good, and being differentiable is good. So all this GELU, logistic, ReLU, even the ReLU is very much used too. Okay, then let's study a bit more this this backpropagation, so this optimization of the weights. So just a reminder how the neural networks are. So you have an input layer. This input layer goes through weights into the next layer, and then the outputs of this layer go through weights into the next layer. And in general, if we call all these weights a matrix W, and all the outputs from the previous layer, we call them L-1. So these are the outputs of the previous layer. We multiply by so this is a vector. We multiply by the matrix of weights, and we add another vector that is the bias, and then we go through a non-linear function that is acting on a vector, and then we produce the output for the next layer. So this is the basic unit in the forward propagation of the neural network. Okay, so in this slide we reason that having non-linearity is a must. So let's say that we have to separate. So we have our neural network. We have to separate this set of points, this set of points. So this set of points, they can be separated by hyperplanes. So if you have two inputs, an hyperplane in dimension 2 is just a line. If you are in R3, an hyperplane is a plane. But if you are in n dimensions, the hyperplane has n-1 dimensions, and the equation of an hyperplane is this one. So a vector times your input value plus b equals 0. Okay, so let's look at the how the information propagates if we allow for non-linearities and if we don't allow for non-linearities. So the first, we will decompose this calculation into two steps. First one is the multiplication by the weights and bias, and adding the bias. So you have some input, and then this input is multiplied by a matrix, and you have some bias, and you have the linear part of the first layer of the neural network. And then you go through the non-linearity. So this is a vector. You go through a non-linear function, and then you have the output. And then you have the next layer. The next layer takes again the input, multiply the input for that layer is this output, but in general it is doing this this operation. You multiply by the matrix, and then you add the bias, and then you go through the non-linear function. This is the output of the second layer, and in this case, because we only have two layers, this will be your output. Okay, so if you compose everything together, so you have the input information multiplied by a matrix, and then adding a bias. It goes through the non-linear function multiplied by a matrix, adding the bias, going through the non-linear function, and if you had more layers, you would have the same sequence. But now let's remove the non-linearity. So if we remove the non-linearity, so this is the first part that is the same as in the non-linear case, but now we don't have this non-linear function. So that means that the second layer is doing the same operation, and our output is just the output of the last layer. Okay, so now let's compose this function. So we have the input multiplied by W1, adding the bias, and then we multiply by W2 and add the bias. So we can expand this expression, so we can have W2 times W1 times the input, and then this term. But this is just, sorry, there is a mistake here. So it is W3 times X plus a bias. So you see that you add many layers, but the effect of having many layers, it is just the same as having just one layer, one linear layer. And this one linear layer is the equation of an hyperplane. So if you don't have non-linearities, all you can represent are hyperplanes. That's all, no matter how many layers you have. So you need non-linear layers to have very complex functions. Okay, so then we need to learn the weights of those nonlinear layers. So to do so, what we will do is to compare our predicted output, that is the output, the vector of the last layer, here represented by L. L is the number of layers we have, and we can compare it to the to the to the outputs that you want, and our comparison will be just the square norm of that. So here, just for simplicity, we have assumed that we have a scalar output, but you can have a vector output, and then this would be the norm of this difference. Okay, so now you have to learn the weights. The weights, you can have multiple weights. Okay, but then a possibility is this gradient descent. So the gradient descent is, you have for every weight in all the layers, you would have to update. One possibility is this gradient descent. So it is you compute the derivative of the cost with respect to that weight, and then you have a learning rate that updates this weight. So what is the reasoning of this? So let's say that we see that when we increase the weight, a particular weight, the cost also increases. So this will be positive. So what we have to do is to decrease our current weight, because when we increase it, we increase the cost. So this term will be positive. So now we will make it a little bit smaller, so that in the next iteration, this weight has a better influence on the output and on the cost that we are computing. So and the same, let's say that it is the opposite. When we decrease it, so that is on this side of the curve. So on this side of the curve, so let's say that we are here, so our weight is too small. So if we decrease it, if we decrease the weight, then the cost increases. Or when we increase the weight, so when we increase the weight, the cost decreases. So this derivative is now negative. So this is negative, and then all this thing, what we'll do is to increase the weight, so that in the next iteration we can have a better cost prediction. And when you are here exactly at the minimum, the derivative of the cost with respect to the weight will be 0, and then you will not change anymore. So this is the rationale between gradient descent. There is this is related to the slope of the tangent, or to the cost according with respect to the weight. So this can have this geometric interpretation of I'm here, and then this part is the slope. So I am approximating the cost by a linear function, and then I'm moving along this linear function by an amount determined by the learning rate. Okay, but now we have multiple layers. How can I compute what is the influence of my weights on the cost at the multiple layers? So we have to do it following the sequence of operations that you will do. So we have decompose it in computing the linear part and then computing the non-linear part. So we compute the linear part. So let's say that I want to compute what is the derivative of the cost with respect to this vector. So it will be the cost with respect to the last operation of the so the let's look at it again. So with set, so with the weights we compute set, and set goes through A, and A is our output. Okay, so our output is A. A has been computed by set going through the nonlinear function, and set has been computed by this linear transformation. So we have to undo that process. So first we compute the derivative of C with respect to A, and then of A with respect to set. This is the nonlinear function, and then from set to with respect to W, and this is the linear part of the function. And what about if we move one layer backward? So if we move one layer backward, this will be the derivative of the cos with respect to W2 will be the cos with respect to A3, A3 with respect to Z3, Z3 with respect to A2, A2 with respect to Z2, and Z2 with respect to W2. But we can observe that this term here is the same term that we had up here. And if you move back and back, further back in the network, so you see that this term is the same that you had here, this term is the same term that you had here, and then you have a similar term. So it is all the time the same structure, all the time the same structure. And you can pre-compute these vectors, or you can compute those vectors and store them in the memory of the GPU when you're computing the backpropagation, so that you can use them to backpropagate this information. So let's look at it in a very simple example. So let's say that this is our whole neural network. So we have two inputs that go through some weights to a first layer, then a second layer, and the last layer. So we will call this output y1. y1 is a function is a function 1 of an argument that we will call it generically we will call it E. So E is the sum of these two weights multiplied by the inputs. Okay, so this is E. This is E for this neuron. And then if we look at the second neuron, so now the weights that we have to use are different, but it has the same structure, and the same for the third neuron. And then we have the fourth neuron. It is the same structure, but now the inputs are the outputs of the first layer, and they go through these weights to compute the E. And the same for the fifth one, and the same for the sixth one. Okay, so now this is our prediction. We compare our prediction, that we call it Y, or we call it Z. We have our prediction, and we compare it to the output. So this output, this is the desired output, and then we compute this difference. This difference is delta, and then this delta is backpropagated. So and then this delta will be distributed into parts. One that has to do with how much F4 contributed to the calculation of this, and then how much F5 contributed to the contribution to the calculation of this. So we have to distribute this delta in here and there, and this delta again is distributed in how much. So this delta is how much we have to change. So we have to change this amount so that the next time our prediction is closer to Y. It would be exactly Y. And so this delta is how much we have to change the inputs here, so that so how much we have to change at this layer. And then how much we have to change at this layer is decomposed into how much we have to change this one and how much we have to change this one. So we have delta 4 and delta 5. And now delta 4 will be contributed by this by this neuron, and this neuron. So we have the contribution of how much should I change this neuron. I should change it by this amount and this amount and this amount, weighted by what are the contributions of this neuron to F4 and F5, and the same for the other two. So you see that at each point you have to add how much you want to change the next layer, and then you back propagate using the weights to how much you should change each one of the previous layers. Okay, so now we can put everything together. So we have how I should change the weights so that the last layer is better satisfied. So it will be the current weights plus some learning rate times what I should change, and I should change this much. Delta is my final error, and this is coming from a particular choice of goal function and structure of the neurons. But then once you have changed these ones, now you also know delta 4, delta 5. So now again you can change now these neurons here. So the weights of these neurons, and it is the gradient descent applied to these weights, and the same for this layer. So actually all the mathematical details, this is the main idea I wanted to convey. So backpropagation is you start with some error at the end. You start from some error at the end, and then you have to compute what is the change I would like to do in this layer, in this layer, in this layer, and those changes will depend on the weights that you currently have to propagate forward. So you use the weights to propagate forward, that will give you an error, and then you propagate that error back using also the same weights. And this particular choice is so why this function here, it depends on what is your cost function and your nonlinear function. And here in this web page that I'm showing here, in this web page it is very well explained, all the mathematical details related to that. But you see it has to do with the gradient descent, and then you have to choose a target. So for the target they have chosen least squares, and then they are computing the gradients. So they are computing the gradients, these partial derivatives of every function. You start from the end, so you start from the error with respect to a particular layer, and then you backpropagate this layer using the rule chain, and you can see, if you want, all the details here, all the mathematical details here, how it is propagated and how you update. Here are the nonlinear functions, the derivative of the nonlinear function. So in our particular case we have chosen a nonlinear function that is ReLU, so that is why so in this presentation that we have here, this presentation that we have here, it is the ReLU, so it is not, you don't have the extra derivatives and so on. But okay, so and here you have absolutely all mathematical details if you want to go into them. But this is already now implemented in all the libraries that we normally use. So these are PyTorch or TensorFlow. They provide automatic ways of computing these derivatives and computing these chain rule and update of the weights and so on. So you don't have to care about them. Here is a code example. I have replicated it here. So if you want, if you go to course data analysis notebooks, deep learning course, one of them that is gradient descent is exactly that. So you can take, this is pure Python code, so you can run it, and let us see it a little bit on the slides. So here we have it. So given, so we will make the neural network a very simple neural network with just one layer, and we will have some input values. So these are the input values. So 0, 0, 1 should give 0, 0, 1, 1 should give 1, 1, 0, 0 should give 0, and so on. Now this is our learning rate. This is the number of nodes in the hidden layer. We just have one hidden layer. This is our non-linear function. So this sigma. And depending on the implementation, sometimes you are required to give also the derivative of the nonlinear function, or it can be inferred somehow in the code. It is numerically estimated. And then we construct here our weights. Our weights, you see, they are randomly chosen. With 0 mean, and they are in the standard in the range -1, 1, and then this +1 here is to account for this extra dimension for the bias. So what we are doing is something like what we represented here. So the bias here can be thought of as a weight with an input that is always 1. So you have 1, then going through W0, and then you can include the bias in this thing. So this would be the dimension of the input. So this is this part here, so in the code. So it is the dimension of the input plus 1 to account for the bias, and then we have these 3 neurons that are in the hidden layer, and then we have some more weights to go into the output. Okay, so now let's implement this gradient descent. So the gradient descent, we will iterate for 10,000 iterations. In these 10,000 iterations, we have to compute what is the output. So we will have a layer just with the inputs. So it is x, and then we are multiplying by this thing. So this thing is just the input plus the bias. Then we have the outputs of the hidden layer. So the output of the hidden layer, it is the multiplication of the input. Sorry, is the multiplication of the input times the hidden weights. We have the dot product of those, so that is Wx, and this plus b is not necessary because we have encoded the bias as one of the columns of our input. We go through the non-linear function, and then we simply stack them. Okay, and then we multiply the output of the hidden layers by the output weights. So this is Wx again, and these weights again has a bias, and so it is just simply Wx, W times x plus b. Okay, and then we are just printing. And then we have to backpropagate. The backpropagation, we have an error at the end, so this is delta, and then we have to compute what is delta in the previous layer, and here it is the derivative that we had. Okay, so this derivative, if you look at the